Hello there, Mr. Sutton here, bringing you this Algebra 2 1-1 lesson on parent functions and transformations. In this one, we will be identifying the function family to which a function belongs, graphing transformations of those functions, and explaining how translations, reflections, stretches, and shrinks affect the graphs of those functions. Before we go ahead and look at some different function families, we should define a few things like what is a function family. So a function family is a group of functions that share key traits or behavior. And out of this whole family, the parent function, which we're going to look at in a minute, is the most basic function of the family. Now, a couple other things that are useful to know are the domain. That's the possible inputs or x values of the function, what it's doing horizontally. And then there's the range, which are the possible outputs or y values or vertical behavior of a function. So with this all in mind, here are splat, 3 different functions that we're going to throw at you. I'm going to have you pause the video in a moment, and using this table with the x values -1 through 1, just plug these into the function, get the y values, and graph these 3 things out. And if you're feeling up for it, see if you can figure out the domain and the range, and then we'll go through it together. So give it a shot. Okay, let's see how you made out here. So this first one, f of x equals 0, always gives you 0 back no matter what you plug into it. So f of -1 is 0, f of 0 is 0, f of 1 is 0. And if we graph these, we get this point here, -1, 0, 0, 0, and 1, 0, which if we keep going gives us a nice horizontal line. Now because we always get a constant value back, this is called a constant function. It's a good name. And it always gives us a horizontal line in terms of the shape. So you might want to write these down. This is how you can recognize a constant function, is by that horizontal line. Now the domain, all the x values that you can plug into this thing and get a value back, it's all the x values, right? From left to right, you can plug in anything and get this number back. So domain, we'll say, is all reals. Now for the range, we can only get a single y value back. In this case, that's 0. So our range in this case would just be y equals 0. Now we have other constant functions out there. We could have f of x equals 1 or some other number, but we just chose 0 this time around. If we picked a different number, the range would change. Now let's take a look at this next one, f of x equals x. If I plug -1 in for this, I just get -1 back. And plugging in 0 gives us 0, plugging in 1 gives us 1. So we've got -1, 1, or -1 rather, 0, 0, and 1, 1. So this also gives us a line, but this case it's going to be a slanted line. So we call these linear functions. And again, a slanted line is kind of the hallmark of these. The domain on these is still going to be all reals. We're going to the left and right forever with no gaps. For the range, however, now we can go down forever and up forever. We can get all the y values, so all real numbers will be our range. And now finally, let's take a look at the absolute value function, is what this one's called. Now if you forgot what that does, it basically just turns whatever value is inside of it into a positive no matter what. So absolute value of -1 becomes +1. Absolute value of 0 becomes, well, 0. It's neither negative nor positive, but whatever. And then 1 is already positive, so that stays as a +1. So graphing these out, we've got -1, 1, 0, 0, and 1, 1. And if we keep going and plugging numbers in, we get a nice little V shape. So again, this was the absolute value function, the absolute value family. You can recognize it by the V shape. That is the feature that the members of this function family share. And then for the range or the domain, we can go left and right forever. So that's going to be all real numbers. For the range, however, we can't get any negative numbers, at least not with the parent function. We can get 0 and everything above that. So we have y greater than or equal to 0 for that range. Now that we've met all those different parent functions, we're going to see what we can do to change them, because if those were the only 3 functions we could ever write, that would be kind of boring. So this idea of a transformation is basically any operation that changes a function's size, shape, position, or orientation. We're not going to do much with orientation in this lesson. That would be talking about rotations, but it's also a thing. So the one we're going to talk about right now is the one dealing with position, and that is called a translation. A translation is going to be something that is shifting a function by adding a constant or subtracting, that's like adding a negative, to all of the x's or all of the y's or both. So to get a grip on what's happening with these translations, I'm going to have you go to Desmos and graph out f of x equals the absolute value of x, and then just see what happens if you add or subtract numbers inside the absolute value and outside the absolute value. So pause the video and have some fun with that. So here I am on Desmos.com. I'm going to open the graphing calculator. That's the one I need. And let me just do f of x equals. And for absolute value, I need the little vertical bar. It's like above my enter, so shift vertical bar. And then I'll put an x in there and close my vertical bar. And lo and behold, there's my absolute value. So let me see what happens if I first add something inside there. Like let's add 2. Oh, it looks like we shifted things 2 to the left. That's interesting. I thought it would go to the right, but it went to the left. Now, if I subtract that same number, now we're going 2 to the right. Very interesting. And then let's say that I can keep that 2 in there, but let me add something outside now. Let me add like a 3. If I add a 3, it looks like that is shifting things up by what I added. And if I subtract a 3, now we're shifting down by 3. So that's kind of neat. So just to kind of pull all that together and organize the information, here's a little table that we're going to fill out. So let's say that we have a function like absolute value and we add a number inside of it. Now we saw on the graph that adding something actually moved us to the left. It was a left shift. Now in terms of what I would have to do if I were to take the x and y values of the parent function and do something to them, if I'm shifting left, I'm basically subtracting something from all the x values. So I'd have to do x minus whatever this thing was that it looked like I was adding in here. Which again is kind of weird that it would be exactly the inverse of what you see, but that's actually how it behaves. You saw it in Desmos. By contrast, if we subtract something, we're going to be shifting right if we subtract something inside. And then we would be doing x plus whatever we subtracted in here to get all the new x values of the function. Now adding outside was a little different. When I added something outside the absolute value, that actually shifted me up, which is exactly what you would expect with this positive here. So now if you're shifting up, you're doing something to the y values. We would actually add whatever that c was to those y values. And then if you subtract something outside, well, you're shifting down, so you would be doing y minus c. So we have this concept of inside changes and outside changes, and they behave kind of differently. We saw here that the inside changes were all horizontal in nature, and they were kind of weird. They behaved inversely of how they appear when you actually plug them in that function. Adding something inside actually subtracts from the x values. Now in contrast, these outside changes were all vertical changes, up or down changes. And those behaved exactly how they appeared. Adding moved us up, subtracting moved us down. So we're actually going to apply this translation stuff in a moment. One other thought I want to leave you with before we move on from this slide, though, is that when you're moving these functions around or otherwise transforming them, transforming a function may sometimes change its domain or range. It might change the x values or the y values that that function has access to. So just keep that in mind and don't assume it's the same domain and range as the parent function. Now that we've gotten some of the theory out of the way behind translations, let's do a little practice. So we've got this g of x function, absolute value of x minus 4 minus 2, and we want to graph this, describe the transformation, and write the domain and range, all those things. So whenever I'm transforming a function whose parent function I'm pretty familiar with, I like to start by making a table with the key points of that parent function. And I do this for any function, not just absolute value. But in this one, we're specifically dealing with absolute value, which if you look back at the beginning, our table that we made with 3 key points, we had -1, 1, 0, 0, and 1, 1. Now, are these the only points you could ever use? No, you could use others, but I like these because they're really easy to plug in, and also this 0, 0 is the turnaround spot for absolute value. So that shows off a key feature of this function. So what are we going to do with these? Our next task is going to be to make a new table with new rules for all these x and y values. And we're going to do that by taking a look and seeing what this function is actually doing with these transformations. So what is this x minus 4 in here doing? Well, since it's an inside change, it's a left-right change. And since inside changes are inverse of what you expect, subtracting 4 actually translates us 4 to the right. Now this minus 2, it's an outside change. That means it's an up-down change, and it's exactly what you expect. So subtracting 2 outside really means going down 2. So once we've kind of figured this out, we're going to change all the x and y values in accordance with this. So what do you have to do if you're going right 4? What do you have to do to the x values? What do you have to do to the y values if you're going down 2? I'm going to give you some time to figure that out. Once you've made a new table, you're then going to graph the new points from this new table, which we'll call the g of x table, and see what that does to our function. And then we'll talk about domain and range after that. So give this a shot first. All right, now that you've paused the video and given it the old college try, let's see what we came up with here. So if I'm going right 4, that means I have to do x plus 4 for the x values. And if I'm going down 2, that means I need to do y minus 2. So what I like to do is just apply one rule at a time for a whole column here, and then I go on to the next one. If I don't have to keep flipping back and forth between the rules I'm applying, I'm less likely to make a mistake. So I'm going to add 4 to all these x values. Negative 1 plus 4 gives us 3. 0 plus 4 is 4. 1 plus 4 is 5. So there's the new x values. For the y values, I'm subtracting 2. So I've got 1 minus 2 is negative 1. 0 minus 2 is negative 2. And 1 minus 2 is negative 1. Let me go to a graph now, and you're going to have to kind of set your own axes for these. I noticed that I'm kind of over to the right, and so I'm going to make my y-axis a little bit to the left just to give myself a little more room over here. So you have to kind of play it by ear or eye, as it were. Let me graph these now. We've got 3 comma negative 1. That's going to be right there. And 4 comma negative 2. And then we've got 5 comma negative 1. And then I'll just draw the absolute value graph through those points because I know what the rest of it looks like based off of those. Now one thing you can do just to double check is look at what you were supposed to do, which was shift it right 4 and down 2, and see if that happened. The original function was on the origin here, and it looks like we have indeed moved this whole thing 4 to the right and 2 down. Okay, what next? So next we wanted to write the domain and range. And you could do this in one of two ways. You could look at the graph and, see what's going on with the x's and the y's, or you could just kind of rely on what you know about the absolute value function. So choose one of those approaches and pause the video and see if you can figure out the domain and the range. All right, let's see how you did. For the domain, we know that absolute value can handle any x value. It can handle negatives, zeros, and positives. Also looking at the graph, we're going left and right forever. So all reals would be our domain. And for the range, looking at the graph, it looks like I can now hit some negative numbers for the y values because this whole thing is shifted down. So I can hit anything that's 2 or higher. Now another way you could do this if you didn't have a graph is you could say, okay, normally the range would be g of x is greater than or equal to 0 because this absolute value has to be at least 0. It can't be negative. But since I have this negative 2 over here, I can throw that in. And now I see doing it kind of this way, using 0 as a stand-in for the absolute value, that we're greater than or equal to negative 2 for the range on this one. Now that we've gotten a taste of translations there, we're going to cover 2 more transformations. Those are reflections and stretches, or they're also called dilations. There's also a 4th one called rotations, but we're not going to hit that in this lesson. So let's start with dilations. A dilation is stretching or shrinking a function, and we do this by multiplying all the x's or y values by some constant number. Now a reflection is kind of related to this. With a reflection, you are flipping a function by negating all of the x values or y values, which is to say we're multiplying them by -1. And I want to be clear, this is a specific type of reflection over either the x or the y-axis. There's other types of reflections out there, but that don't behave kind of like this numerically, but we're not going to worry about those for this lesson. So, for just dealing with these two things, go back to Desmos with absolute value of x, and now let's see what happens when you multiply by both positive and negative integers and also fractions inside and outside this absolute value. So mix up the numbers, throw some fractions in there, give it a shot. So here I am back on Desmos, and let me see what happens if I just multiply by 2 inside here. So when I do that, it looks like it's kind of shrinking me horizontally, if I think about inside stuff as being a horizontal change. And then if I multiply by 1 divided by 2 instead, that stretches me horizontally. All right, what happens if I multiply by something outside? Now this is going to be a vertical change because it's outside. If I do that, it kind of looks like a horizontal shrink, but what's really happening is we actually have a vertical stretch. And they look exactly the same to some extent, but it's vertical. So now we have 1/2 outside. That's going to shrink us vertically. Now what happens if I do some negatives? So if I put a negative outside, that's going to flip me vertically. And if I put a negative inside, that's going to, ooh, it looks like it does absolutely nothing. But here's the tricky part. Let me show you a different function now. So let me do square root, SQRT, because this one it's easy to see. Here's the initial square root function. Now if I make the inside of that negative, it looks like we are flipping horizontally in that case. We couldn't really see this with absolute value because that one's symmetrical, but we can see it with a non-symmetrical function like this one. So just to sort of recap all of that and put it in a nice table, and so this is what's happening with my graph if I take some constant that's bigger than 1 and apply all these different situations. So multiplying by something bigger than 1 inside is going to shrink us horizontally. And what's actually happening is you're not multiplying all the x values by c, you're actually dividing all the x values by c, which is to say you're multiplying them by 1 over c. That's what's really happening to cause that behavior. Now, if you multiply by a fraction inside, that's going to give you a horizontal stretch. And then instead of dividing by c here, you're actually multiplying all the x values by c. So again, it's inverse of what you expect because it's an inside change. Now, the outside changes, a number bigger than 1 outside gives us a vertical stretch, and that's going to be c times the y value. We really are multiplying by c in this case. Dividing by a number outside gives us a shrink vertically. So 1 over c times y would be the rule for that. And then if we have a negative inside, that gives us a horizontal reflection, which we couldn't see with absolute value, but we could with other functions. So that's going to change all the x values to negative. It's going to negate them. And then a negative outside the function gives us a vertical flip, which gives us all negative y values, or negative of what they used to be. If they were negative before, now they're positive. So one thing, again, to keep in mind is that reflections may not show if a function is symmetrical, especially over the y-axis. If it's symmetrical over the x-axis, then it's not a function because it fails the vertical line test. So just to make things interesting for this next example, illustrating a dilation and reflection, we'll do a real-life problem here. So this is Maria. Hi, Maria. She unknowingly signs up for an app that is automatically charging her $4 a day. Now let's assume that she has a bank balance of 0 on day 0, which is pretty unfortunate. And let's also assume her bank is going to let her maintain a negative balance instead of just not going through the transaction. We want to write and graph a function that represents her balance after X days. Okay, so pause the video for a minute and see if you can come up with a function that basically subtracts $4 a day. So a function we could use for this, if we just take the number of days and multiply by -4, that'll give us how much money we've lost. So we can just write g of x equals -4x. Now, in terms of function families, this is going to be linear. It's basically an x to the first power. It's something times an x. So this is our parent function, y equals x. And the table for that, initially we had 3 points, but we don't really need 3 points. If you're graphing just a line, you really only need 2 points. So I'm going to use 0, 0, and 1, 1. We don't really need more than that. So in a minute, I'm going to set you loose to transform this thing based on what's happening here. One thing you should keep in mind with lines, they're kind of a special case. There's no inside versus outside with lines. Everything is kind of outside of the function, which is just this x here. So all linear transformations can be expressed vertically by just messing with the y value. With that in mind, pause the video and see if you can make a new table and graph this thing. All right, so for my new rules here, this is going to be a vertical reflection because I have this negative, and also because I'm multiplying by a number that's bigger than 1, this is going to be a stretch vertically as well. So making my new table, my x values don't have to change at all, right? We're not messing with x for this one. But the y value needs to change. So this -4 means I'm going to have to do -4 times y to get this. This is all vertical stuff happening. So my x values are still 0 and 1. For the y values now, well, -4 times 0 is still 0, so that doesn't change, but -4 times 1 is -4. So graphing these out, we've got 0, 0, and 1, -4, and then just draw the line through those. And that's Maria's bank account. Not a pretty picture. At this point, we've done a little bit of every transformation. It's time for the final boss battle. This one's got a lot of transformations going on. Now hold on before you pause the video and try it on your own. One little piece of advice, because this has some stretches and translations going on. And that piece of advice is that stretches and also reflections, while we're talking about it, are going to happen before translations. Because in PEMDAS, multiplying happens before addition. So we have multiplying transformations before addition transformations. With that in mind, give it a shot and let's see how it goes. All right, so this is the absolute value function, pretty easy to recognize. So my parent table of that is again -1, 1, 0, 0, and 1, 1. And in terms of transformations, this -3 out here is a reflection and a stretch vertically. The 2 inside is inverse of what it looks like. It's actually going to be a horizontal shrink. We're actually dividing all the x values by 2. And then this +1 outside, we're adding 1 to y values. That's a translation up 1. So for my new table rules, for x, again, we said we're dividing by 2. That's going to be 1/2 x. For the y's, I'm going to write this as -3 times y. That has to happen first. And then I'm going to add 1 to that result. So again, multiplying before addition. So plugging all this stuff in now, we've got 1/2 times these x values. That's -1/2. 0 is still 0, and +1/2. Now we have -3 times the number plus 1 over here. So -3 times 1 is -3, plus 1 is -2. -3 times 0 is still 0, but plus 1 gives us a 1 here. And if we plug 1 in again, we still get -2 because we already kind of did that. All right, let's see what this looks like if I graph it. So we're going -1/2, -2, that's down here. We have 0, 1, so that's going to be up here. And then 1/2, -2. There you go. So let's graph that. So this is an upside down absolute value, so that reflects the reflection we expected. We stretched it vertically. It looks like that happened. And we also, after doing all that, translated this whole thing up 1. So we hit all our bases there. So that's it for this lesson. Hopefully it has been a transformative experience for you. Until next time, this is Mr. Sutton signing off.